The second team is Team 5, Sailboat Bailers, and their customer is Professor Mark Horenstein.
All right, so we are the Boston University Boat Bailers. This is Alex, Henry, Mason, and I am Andy. So the problem that we are trying to solve is that a lot of sailboat owners that don't live close to where they moor their boats have an issue of flooding in their bilge when it rains and the water builds up. So our solution is design a solar-powered sailboat bailer that reports information on the depth and the battery charge to the user. One of the problems is the user can't come to the boat and change out the battery when the pump runs out, and the pump takes a lot of power to run. This is a basic overall block diagram. We have two inputs: the water level, environmental energy, which is our solar panel, and the outputs would be mechanically removing the water via a pump, and the radio reporting device. A little more in depth here. You can see we have a water sensor that reads the water level, goes to the microprocessor. We also have a solar panel, a charge controller, battery, and once again, pump and the radio are the output. Here's the overall schematic for our system. We're going to go a little bit more in depth into each part.
All right, a big part of our project is to keep the boat bailed while adequately charging our battery. And for our system, we're using a 12-volt, 18-amp-hour deep cycle battery. And our pump is a 5.5-amp bilge pump. And based on the battery that we're using, it can run up to 2 hours on a single charge. To put into perspective of how much energy and how much bailing that is, the annual rainfall of Massachusetts and Marblehead is around 49 inches. And given that the boat's bilge is around 37.4 gallons per inch of rainfall, and that we're using a 1,000-gallon per hour pump, the system can bail out optimally 53 inches of rainfall. Realistically, the actual thing will be around half a year instead of a full year on a full charge. And if we're looking at the recharging part of the system, our solar panel runs at about 1 watt given 12 volts. And on average, there's about 8 hours of sunlight, which equates to around 1/3 watts for the entire average day. And if you know the power and the voltage, you can find the current, which is 27.7 milliamps. And from there, you can find that it will take around 27 days to fully charge a 12-volt, 18-amp-hour battery, assuming that there's not too much like sunny days, like not too much cloud and things like that. So most of the power budget is based on the solar panel, the bilge pump, and the battery. So depending on how big the boat is, we may have to change what kind of how much power the solar panel gives and the battery and such as that. And pass it back to Andy.
So I designed the depth sensor. The reason I chose this design was because a lot of depth sensors that you can buy online can go up to a few $100s, depending on how accurate they are. So what I have here is I'm using a air pressure sensor. It's a differential pressure sensor, so it has a differential input and the pressure input, and it has a film that measures the difference in pressure. So what we're doing is attaching one tube, the pressure tube, to the pressure sensor, and then putting it in the bottom of the bilge, so any water level that rises up sends pressure up through the tube and can be read on the pressure sensor. Also, you can see the ambient tube has to be out in the air to differentiate. This is my circuit, basic amplifying circuit. You can see I have 2 potentiometers. One of those is gain, one of those is offset. The main reason we're using potentiometers and not set resistors is for different boat sizes and different amounts of accuracy. So if you want if you have, say, 2 feet of a 2-foot bilge, then you could measure up to about a half an inch accuracy, or a 5-foot bilge we have right now measuring up to an inch of accuracy. The output obviously is linear, so every inch can be 0.1 volts, and that output is then sent to the microcontroller and read as a depth.
So unfortunately, our 5th group member could not be with us today. Srilalitha couldn't make it, so I'll hopefully not too haphazardly try to cover her slides. I'll note which ones are hers. This is one of hers. This is basically the power curve for our particular solar panel as we tried to characterize it as best we could on a sunny day. You'll notice that there's a very clearly defined peak of output power that's not at either the short circuit current or the open circuit voltage. So you can't just arbitrarily pick where to operate a solar panel. And in fact, this curve will vary amount of insulation and so on. So given this particular panel at this particular time of day, we note experimentally that we get a peak power of around 750 milliwatts if we're operating the panel at roughly 10 volts. So this gives you an idea of what we need to accomplish in terms of trying to get the maximum energy out of our solar panel possible. We need a system that looks for this power point and operates at it at any given time. So we'll get into how we do that. This is the sensing side of our maximum power point tracking system. This actually isn't completely accurate. The voltage sense and current sense are actually after the buck converter, because given inefficiencies in the buck converter, given characteristics of operation, we don't actually so much care how much power we're pulling out of the solar panel. Our real goal is what we do with the power. We want to maximally charge our battery. So what we really want is the maximum power going into the battery. So by measuring after the buck converter, we can maximize the actual work that our circuit does. And then we have an algorithm monitoring these two sensors in order to actually affect change on our buck converter performance. So a lot of these are relatively difficult to read, sort of small type. The overall gist of it is pick a power point, operate at it, see what power we're pulling out of the system given that particular current that we're driving into the battery, and then perturb and observe. So step up in output current. If the power also steps up to match, then we know the solar panel can be outputting more power and we should continue in that direction. And similarly, if by stepping up the output current we actually negatively impact power, we know we need to step back down in the other direction. And then this is the action side of that circuit, where we actually change the output power. It's a simple standard buck configuration. We've actually used a PMOS as the switching element just for ease of implementation, rather than having to integrate a charge controller, although in a more costly and complex system you would generally use an NMOS there instead with a charge controller, or charge pump rather, to drive it. In this case, we simply have a PWM input. When that input is high, the PMOS is turned on and we're driving current into our regulator. And when that turns off, we stop driving current into the regulator and allow buck operation. And standard buck converter procedure, by driving it with a PWM, output is related by duty cycle to the input voltage. But we also need to measure the actual output current, and this is the circuit that we're using to do that. Again, this is Srilalitha's circuit, so I'll try my best to describe it without messing things up. We're using an AD8210 differential. It's intended to be a current sense amplifier. Based on the shunt resistor used to measure current, this amplifier will have an output voltage gain of 20. And then next to it we have an 8603, which is just a simple op amp to handle appropriately setting the output voltage. You might wonder why we actually need an op amp to buffer that voltage divider. This particular current sense amp, for whatever reason, actually has a low impedance reference voltage input, so it's necessary to buffer it with this external chip. This amplifier just gives us a nice output offset of 1 volt, so that we're not operating anywhere near cutoff points. And it will amplify based on our shunt resistance. Currently our shunt resistance is 0.33 ohms, therefore 0.33 times a gain of 20 is 6.6 ohms, from which we can calculate our actual current incident through that sensor.
All right. So the microprocessor that we're using is the ATmega, and the main objective of this microprocessor is to pretty much read and record water level, the battery voltage, the battery current, and the solar panel voltage. Then it uses these values to basically do more important functions, such as determining whether to pump based on the water level, or finding the maximum power, or tracking the maximum power point on the solar panel. Here is just the power regulation support circuitry for the microcontroller. The only thing that's added there is the FTDI breakout board, which is mainly used for demoing and debugging, etc. The next component of our system is the pump driver. The actual device that's used to drive the pump is BTM7752G, which is Infineon's H-bridge. It's so basically it interfaces between the microprocessor and the pump, and basically when the microprocessor reads that the water level has been reached or whatever, then it will output a signal to this H-bridge, which then connects the battery to the pump and drive it. Yeah.
And so the final component of our project is the radio reporting interface. We chose to go with a GSM cellular module for flexibility and ease of integration with general lifestyles of the people using the system. We had toyed around with some other ideas that were all either too bulky or too costly or too short of range, and so on and so forth. This is a nice happy medium where generally boats moored in a harbor have relatively good cell coverage. Certain harbors less so than others, but very few integration problems there. The module that we're using, the module on the bottom picture there, the back side of this board, is actually a BenQ M32 GSM module. So it's a commodity part, highly available, relatively easy to integrate and relatively used, so there's a lot of precedent for it. And it just happens to be integrated onto a carrier package in the form of a USB module for use with a computer or whatnot. We've simply taken apart the serial interface and disabled USB functionality of it such that we're only using the M32 module on the backside. It's relatively easy to actually operate. It uses a standard AT command interface, as most cellular radios tend to. The only sort of hassle with integration is that the board, while using a 5-volt VCC, happens to operate at 3.3 volt levels. So all we had to do was use a simple level shifter on the output line of the microcontroller so as to prevent bricking the board. Beyond that, we simply output AT commands to the device, and we can measure responses or simply ignore them and attempt to send text messages brute force. Currently what we've implemented is sending text messages. However, we're also capable of interacting with web services should that be a point of future expansion. We can query websites, add data to web services, pull commands down, and so on and so forth. It's a very flexible interface. Unfortunately, I'd like to note you won't happen to see us sending any text messages in demo because AT&T doesn't like us very much. AT&T doesn't like photonics very much, it turns out. This is just a sort of overview of our actual layout. You can only really see the top layer here, but it's only a 2-layer board. The bottom layer is slightly visible and also not extremely interesting. You'll also notice that there are 2 unplaced components in the bottom left. I'll point those out as well. The reason that they're left unplaced in this layout is that they were actually added a revision after we submitted the board for manufacture, so they're reworked onto the bottom side of the board. We just added a filter between the current sensor output and the actual microcontroller input because the current output happens to be relatively choppy and we're not oversampling it at all. So we would like to get a DC set point rather than know what the actual current waveform is. And then this is our board implemented, which you can see in the demo area functioning. Any questions? Yeah.
What's the depth in the built-in set action trigger currently, or is that variable?
It's variable because it's in the code. Right now for the demo we have the pump turning on when the water exceeds 6 inches and it shuts off when it goes below 3. So you can see we have it hooked up to a meter stick, and when it goes past 3 inches you can see it turn on. There's also a little bit of a delay in there right now. I believe it's about 5 seconds, so I think that's to save power. Anything else? Yeah.
So if I understand correct, since you're using GSM in this case, right? You would need to subscribe to some service and pay a monthly bill fee in order to be able to use it, or that's a workaround?
Yeah, no, it does cost a nominal fee. We decided that rather than go for an alternative option, which might have been something like a APRS packet radio service or something along the lines, it was worth it to us and generally our users to, rather than deal with a bunch of bulky equipment. Lots of boat owners have radios and whatnot, but relatively few of those radios actually support packet services and so on, and that also requires having a base station in one's home. It was sort of worth the $10 to $15 per month maximum cost for a basic implementation, rather than have to deal with bulky radio equipment. Depending on which carrier you go with, for a simple implementation, text messages are 10 cents a piece, pay as you go. Internet options abound, but generally you can get a basic, low bandwidth connection for a few dollars a month. Because we're not sending massive amounts of data, just control signals and such, really the most that you could possibly use is, a few dollars worth of data, even at a few cents a kilobyte.
What's your estimate of the cost of this?
Oh, sorry, the cost of the overall system. That's true, we actually didn't mention that. The overall system, our target price point based on a particular competitor that we found that doesn't have quite as full a feature set was $250 to implement pump, panel, casing, board, everything included. We ended up meeting the price point of about $200, even including nominally priced panels, pump, and so on, which we were actually given for the purposes of the project. And then the bill of materials cost for the board itself is whatever it costs to produce the PCB. In our case, it was $30, but in mass production, it's on the order of $1 or 50 cents or so. And then a BOM cost of roughly $35 to $40. Yes, Professor?
Did you measure the surge current when the pump is turned on?
So, in fact, that is, yes, a bone of contention. So we have not measured the actual surge current when the pump turns on, or for that matter, the freewheeling voltage when it turns off. Our motor controller, our output H bridge, actually, Mason, you can talk more about this, but.
Or what, the H bridge?
Yeah, the H bridge drive characteristics.
All right, so, right now, the H bridge has 2 high side P MOSFETs and 2 low side N MOSFETs. Those, the problem with, actually I mentioned this earlier, but the problem right now is that the H bridge currently output the continuous current of the H bridge is 4 amps, whereas the pump itself is 5.5 amps. So our way of fixing that was to set a PWM signal to the H bridge, not 100% duty cycle, but say like 50% duty cycle, so that it won't burn out the chip. I'm not sure if that was your question or not, but yeah.
There's also one more consideration, which is presuming your pump is too high a current to use with our H bridge itself, we don't need to actually propel the boat, so 1,000 gallons an hour is an unnecessarily high mark. You can use a much smaller bilge pump that fits within our H bridge specs, no problem. But if you happen to be using a much higher current device, it's also very easy to drive a relay, which is what we have set up out on our demo area.
One more question, Elias?
Yeah, I have 2 quick ones. These lead acid batteries, you have to get a threshold to meet the trickle charge requirement. Otherwise, it never really charges. Did you solve that problem?
In terms of the maximum or like minimum output current and whatnot, the answer is no, because there's not a way to guarantee a minimum output current. Our algorithm essentially shuts off should there not be sufficient current to additionally charge the battery. And at worst case scenario, it's simply not draining the battery. There are reverse protection diodes just to try to prevent leakage current.
So you have a trickle threshold set up, and if it's going to be below, you just cut off.
Essentially, yeah.
Yeah, that's fine. Then the other question is, given that you mentioned the lifestyle of the folks that have this, Wi-Fi seems to be very available, and the masts made for a wonderful antenna.
That's an interesting point. I hadn't considered integrating an antenna for Wi-Fi into the mast or anything like that. That certainly would be an interesting thing to consider. We had initially ruled Wi-Fi out, just because generally speaking, your marina will have free available Wi-Fi access, and presumably you can request access if it's not free. But range was certainly a problem. Using the mast as antenna is actually a very interesting idea.
Not only that, I mean, you can put an RG9 coax with virtually lossless through the mast.
Yeah, the larger problem in that case is increased initial cost, but yes, it's certainly an option, and for a commercial product, we should certainly offer both, for that matter.
Thank you.